Hi there, welcome to a presentation on implicit differentiation. In this presentation, I would like to sort of explain what we mean by implicit differentiation, where do we use it, and when do we need to use it, and compare it with the usual differentiation we do, let's say at school, or the differentiation we start with from when we introduce differentiation to. Okay, let's then start this way. Now, I've given you here two equations which apparently they don't look exactly the same equation, but they are. What I want to explain in this case, I want to explain the difference between the terms implicit and explicit. When functions are introduced to us at school, they are given in this form, like you can write it as y is equals to f of x. In this case, you can say f of x is equal to 3x plus 2. The reason why we give functions this way, I think you can see here we've got independent variable x, which is represented by the horizontal x on the horizontal axis, and the values of the functions are taken along the value or the vertical axis, which is y. So a function like this would plot it on a system of coordinates we call the x y system of coordinates. So that's why we put it here as y is equal to f of x. If our variable x, let's say it represented time, then we'd write this as y is equal to f of t. And then the horizontal axis then will be time, then will be represented that on a ty system of coordinates. But then what we basically mean here that if we've got it this way, it means that we can plot the graph of the function, whether maybe it's a straight line or it's a curve of some sort. We can plot it on the x, y system of coordinates. So now if we give a function in this form, like we have got it here, we will say the function is given explicitly. Now it is an explicit function which is sort of self-explaining how to get the values of the function y. In many words here, to get the values of function y, we need to multiply the independent variable x by 3 and add 2. So that is explicit. But if I give you an equation this way, when we've got this equation this way, it's a linear equation, we still have to understand here that y is a function of x. So the fortunate part of this equation is that this equation, though it's given implicitly, we can manipulate it algebraically until we've got it looking given in an explicit form. In other words, we can add on both sides here 6x, we'll get this as 2y is equals to 6x plus 4. And we divide both sides by 2, you can see that we've got this as 3x plus 2, which is exactly the same function as that one. So in this case here, the function is explicit, and this way the function is given implicit. So in terms of differentiation, there's not really a difference in doing implicit, what we call implicit differentiation. We call it implicit differentiation just because we apply it to differentiating functions which are defined implicitly. But it's not always easy functions like this which you can easily convert to the explicit form. But now what I'm going to do now, I'm going to take this function as it is, and I suppose you know how to differentiate it. I will differentiate it using explicit differentiation, and then differentiate this one using what we call implicit differentiation. So let's look at this. So we've got here y equals to 3x plus 4. So I'll use power rule here. And then if we say now dy dx here, dy dx is just a simple notation to indicate that we're differentiating a function y with respect to the independent variable x. So if we use power rule here, our power there is 1. So what do you do now? You have 3 here, then you have a 1 there, and you have x to the power 1 minus 1 plus the derivative of 4, which is a constant, which is 0. Then here we're going to end up with what? 3 times x to the power 0, which gives us 3. That's how to differentiate that function. That differentiation there, normally when you introduce it, you don't even mention that the function is explicit, but essentially the function is explicit. It's only when we start to have functions which are defined implicitly, then we start to make this differentiation, to differentiate between what type of differentiation we're doing. So on the other hand, we're given the function 2y minus 6x equals to 4. So now here, y is an implicit function. When I've got this function as it is like this, in the background, I should understand that we've got 2y, a function of x, minus 6 times x equals to 4. So when we're going to differentiate applying this method of implicit differentiation, what do we do? We basically do what we call term by term differentiation. Now as we're going to come to this term and differentiate, visit this term and differentiate, and visit that one and differentiate. Then at the end, we must then determine our dy dx, which is our final target. So how do you do that here? So when I come here, at this stage here, I suppose I don't know exactly how y looks like. So when I differentiate here, we'll simply write 2 dy dx minus, when we come here, we differentiate, we get a similar answer to that, we get minus 6, and then this will be equals to 0, because the derivative of 4 is a constant, the derivative is 0. So now remember, our target is to get dy dx. And here we've got an equation which has got dy dx as an unknown. Then we solve for that unknown. So what we're going to get here, we add on both sides 6, then we get 2 dy dx equals to 6. And then as you can see now there, we've got almost like a standard equation like 2x is equals to 8. So all what you need to do here is divide both sides by 2, because our known here is dy dx. So dividing both sides by 2, we get dy dx is equals to 6 divided by 2, which is equals to 3. So as you can see now here, dy dx here is 3. We arrived at 3 applying implicit differentiation. So what is actually implicit here is the function which is defined implicitly. Then with the differentiation we apply there, we call it implicit differentiation. But dy dx is the same notation which we've been using before we introduce the term implicit differentiation. So as it is here, the function was defined explicitly. So this is an explicit function. And then we defined it, we differentiated it the usual way we do our differentiation. And now here we have the function given implicit. This is an implicit function. Then we differentiate each and every term in the equation there, and then finally make dy dx subject to the formula. Then we say we're doing implicit differentiation. But like I said before, this equation, these two equations in particular, is the same equation. The one we're given implicit and the other one given explicit. But we can see that we can always manipulate it to get to explicit. But there are some cases which we cannot express y explicitly. Like for example, these are two examples of functions which are defined implicitly, and you can never express them in an implicit form. Like for example, if you try to make y substitute the formula in this equation, you will see that you will always have y on the both sides of the equation. Similarly, there you have got the same situation. So what we have here is that we suppose that function y is a function of x. And being a function of x, we can plot it on a xy system of coordinates. Maybe it's a curve which could go maybe something like that, just for example. So if it's a curve like that, using implicit differentiation, we can determine dy dx like we've seen before. And we know our interpretation of a derivative at a point that it gives the gradient of a tangent line. So then, without necessarily knowing the function in an explicit form, but assuming that it has got a curve like this, and maybe we choose a certain point, let's say x0, we could be interested to finding out what is the equation or what is the slope of the curve at that point x0. In this case, we'll be talking about the slope of the tangent line at that point x0. So the fact that the function is given implicitly, it doesn't stop us from determining its slope or determining its tangent line or normal line. So now, if we have this function, we first of all, to determine the normal line or to determine the slope, we first of all need to differentiate this function implicitly. So what do we do? One thing which we mustn't lose sight of, all the rules of differentiation apply here, whether it's power rule, quotient rule, product rule, they will apply. So let's start with this example. Maybe I'll leave the next one for you to do as your own example. Then, if we start this with this example right here, x squared plus 3xy plus y squared is equal to 6. So what we have here, we've got a function y, a function of x, which we don't really know its expression, is explicit expression. So it's just given here implicitly. So if we were to find the slope or find the equation of a tangent line at a given point, we will first of all need to determine dy dx. So we come here and differentiate this implicitly. Like I said before, we go and differentiate each term at a time. So if we come here, we'll differentiate this using power rule and say 2x. And then when we come here, it's like we've got two functions. Actually, not like we've got two functions. A function which is we can call y of y equal to x, and another function y which we don't know how it's defined. It's just known to be a function of x. So what we need here, we need a product rule because this is a product. So what we have here, we get 3 in brackets. We can differentiate x here with respect to x, differentiate x with respect to x, which will give us 1. So we've got 1 there, multiplied by y without differentiating, plus x multiplied by the derivative of y with respect to x. That's what we've got there. We've just applied the product rule. Then in this term here, would again apply chain rule. Now is apply power rule, say 2y, y to the power 2 minus 1, multiplied by the argument of the power function here is y. Then you multiply by the derivative of the argument of 2, which is dy dx, and then we get this equals to 0. Then now we've got dy dx in our equation. We've got to make it subject to the formula. So we just have to reorganize this, and then we've got here 2x plus 3y plus 3x dy dx plus 2y dy dx equals to 0. Then you can see that common factor here is dy dx. Then you can take it out as a common factor, dy dx, and then we've got 3x plus 2y equals to minus 2x minus 3y. As you can see here, I subtracted on both sides 2x plus 3y. Then you get that. Then finally, we've got dy dx given as minus 2x minus 3y over 3x plus 2y. So that will be the expression of the derivative of this function, which we don't know how exactly is defined explicitly. So then we know that if we're given a point, let's say we're given a point x0 equals to 1, and then we are asked to find or determine the slope at when x is equal to 1. Then to evaluate this, obviously you can see that we need the value of x and we need the value of y. So maybe to get to find the slope, we would need to given also the value of y. So then we can assume here, let's say the value of y at x equal to 1 is equals to 0. So if we do that, then to find the slope in this case here, we would say the slope, let's call it m. It will be to evaluate the derivative with respect to x when x is equals to 1 and the y is equals to 0. So then what we have to do in that case, as you can see, this, what I've given here, it does not really describe this figure, because you can see that the value of y here is not 0. I think you can see that. So, but for this is just for to save an example. Let's say we're given a point like this. In other words, if we're saying this, we're basically saying the curve of the function passes through a point which is 1, 0. So then if we evaluate here, what we do, we then say substitute x by 1, then we get here 2 multiplied by 1 minus 3. Now here we have the value of y at 1 over 3 multiplied by 1 plus 2 times the value of y at 1. But already seen that the value of y is 1, 0, so we put 0 here, 0 there. Then the final answer here will be 2 minus 2 over 3. And then in that case, if this is the gradient of the tangent line, then which means the equation of the tangent line will be y is equal to minus 2 over 3 times x plus c. And of course, this will be the point of tangents, which is on the curve and is on this line. So that point must satisfy this line. Then we use it to find c. Then what we can do there, we just put 0 there, equals to minus 2 over 3 times 1 plus c, which you can solve and get that c is equals to 2 thirds. Then you can write the equation now as minus 2 thirds x plus 2 thirds. That would be our equation, the equation of the tangent line. And then you can proceed, maybe find equation of the normal line and so on. But essentially, implicit differentiation and usual differentiation, which you know before from school, they are not different. The only thing which is different is that the functions, the way they are defined, is not the same. At the beginning, when you start differentiating in school and basically at level 1 mathematics tertiary, we deal with functions which are defined explicitly, and we learn all the rules of differentiation. And then when we now get to situations where we got expressions like this, where we cannot express y in terms of x explicitly, we just call them implicit functions. Then when we differentiate them, then we call that differentiation implicit differentiation. So now what I'm going to do now, what I said to you, I'm going to leave this example for you to attempt. As you can see already, you've got a product of two functions, function y, which is not given explicitly, and now you've got to apply chain rule, because you've got sign of a product of two functions, x and the y. And then from there, you can practice from your text and do all sorts of things like determining equations of tangent line, normal line, and so on, and even many other applications of differentiation you can use applying this implicit differentiation. Otherwise, at this stage, I would like to say thank you for listening. I hope this helps, but if you've got further questions, please post your questions on our tutorial platform or on my Unisum. Bye for now.